Welcome, guys. We're going to do another example here from the notes of just some of these yucky irrational graphs and kind of how you approach problems like this. So problem number 24, we're dealing with b of x, so good old Bob here. Quadratic over another quadratic, so x squared plus 4x plus 3 divided by x squared plus 7x plus 12, okay? And remember, you can't cancel terms, so this is stuck in the form that we are at, but luckily, I think we should be able to work with this a little bit. If we factor the numerator and the denominator, we can break it, hopefully, into groups that will maybe cancel. And so we need to multiply here to be 3, and then add up to be 4. And so the correct combo is 3 times 1 and 3 plus 1. And then the denominator, I'll do that off to the side here, is multiplying to get 12 and adding to get 7. 4 times 3 and 4 plus 3 fit the bill on that side of the problem. And so we can kind of put this all back together again, that this is really your fraction with the groups x plus 3, x plus 1, over the groups x plus 4, x plus 3. And we should always kind of note, is there anything that's able to cancel once we group things out? And the x plus 3's absolutely do. And that's my first thing that I always look for. I look for holes. In the act of canceling those two factors out, I am creating a hole at the x value that would make that 0, so at x equals -3. And usually I will take that and I'll put it somewhere on my graph. That way I remember to not fall in my hole. So there's a hole somewhere along this like vertical strip of the graph. Next, I like to go ahead and talk about the x-intercepts. I think that's pretty easy. Those come from the thing that's left over in the top. So let me write the fraction that is left over. X plus 1 divided by x plus 4. Okay, so we can see from the numerator right there that my x-intercept is going to come from -1. -1 plus 1 makes 0. -1 plus 4 makes 3. And 0 over 3 is 0. So an x-intercept at x equals -1. Those only come from the numerator. The denominator, the bottom of this fraction, creates our vertical asymptotes. And I think that's the third easiest step. So if I look here to try to figure out what I don't want to divide by, you never want to divide by 0. And -4 as an x value would create that situation. So I have a vertical asymptote at x equals -4. That will also be one of my restrictions. That's an x value you want to avoid. Then I think the hardest part here is moving on to the horizontal asymptote. Horizontal asymptotes just have a lot of rules that kind of change depending on your situation. And so if we go back and look at our original problem, this is a quadratic over a quadratic. So you have the same degree over the same degree, and that's kind of an interesting setup to have. One thing you can always do to almost determine where your horizontal asymptote will lie is you start to consider what happens when x gets big. If it gets further and further away from 0, these terms towards the end, the 4x and the 3, the 7x and the 12, they matter less and less and less because squaring a big number really is the biggest chunk of your answer. And so this ends up, as x goes to positive and negative infinity, really looking like x squared over x squared, which if you cancel those things out is equal to 1. And so my horizontal asymptote is going to approach that ratio. It's going to approach y equals 1 as I go further left and further right. It's just which side of that asymptote we're approaching from. So that's kind of a nifty little trick. I typically like to suggest that when you are doing these problems, maybe support that horizontal asymptote conclusion with some long division. Okay? Long division can help show you different structures that we might not see just from the information that I've jotted down here on the side. So you have to remember that process for long division and how it works. We are going to be doing long division with what's left over because that's what I'm going to end up seeing out here on the graph. So x plus 4 is what I'm dividing by. And then I'm dividing that into x plus 1. So here we go. X times what equals x? Well, x times 1. 1 times x is x. 1 times 4 is 4. And that was a positive. If you remember the long division process, I put parentheses around that group because I'm subtracting it all away. And so x minus x should always give us 0. If we aren't getting 0 there, we aren't doing our job. And then you have 1 subtracting 4, which is negative 3. Then you ask, can x make negative 3 a constant? Nope, this is too big. And so I know the process is done. This negative 3 actually is my remainder. And we write our remainders up top as a fraction. So I would have negative 3 over the divisor, so this x plus 4 group. And typically this is actually written kind of backwards from how we are focusing on things this chapter. If you kind of flip things around, you'll have negative 3 over x plus 4, and then this 1 being a positive 1 comes at the end. Okay, so the sign that's in front of that number just always precedes that. And this should make a lot of sense to you. This reveals some structure. I have a reflection. I have a stretch because 3 is larger than 1. I'm moving this graph left 4. And then the plus 1 at the end is shifting the whole graph up 1. So if you do long division, this process, you can sometimes reveal that your graph is actually one of these simple rational functions that we did early on. You should always be able to graph something like this without using an XY table. It's when you start to get things that don't work out so nicely that you have to put x and y to justify some of those point coordinates. But we know everything about this. This is a pretty easy graph to do once you long divide and kind of see that process. So a few things. Whatever is left up in front of the long division process, this is your horizontal asymptote. Weirdly enough, you can get quadratics here. You can get almost any shape in that location after long division. The rational part is it lays on top of that horizontal asymptote. It approaches the horizontal asymptote as you get bigger or smaller. If you rearrange it, the up 1 moves our horizontal asymptote up. And so all of these pieces of information should agree with each other. Okay, you should be able to confirm this. So I like to go ahead, let's put our x-intercept on the graph. I forgot to do that earlier at negative 1. Let's put our vertical asymptote on the graph at negative 4. So we'll draw a vertical line and then we'll make it dashed. And then our horizontal asymptote happens here at 1. So I can go ahead and draw that in and make it dashed as well. These, again, are invisible, but it's good to put them on your graph because they give you guidelines of where to go. So back here, okay, understanding that we have a reflection, understanding that we have a stretch. I go to the center of the graph. Okay, before I kind of taught you guys to put a star here. It's not a point, it's just where we start. It's a relative center, if you will. And I'm going to count out 1, 2, 3 from the center. And look, I already have that point because that actually was my x-intercept value. And then here we're going to count 1, 2, 3 down and put another point. Okay? These simple rational graphs, it's just counting. 1, 2, 3 stretched over here in this other quadrant, the opposite quadrant, and 1, 2, 3 out. Okay, so if you don't remember kind of how to do those graphs, go ahead and review your first set of notes. These are the simpler ones. I think people did generally pretty well in that section. So then we can go ahead and draw in our two curves approaching the asymptote in that area of the graph. All right, so overall, this actually turned out to be a pretty easy thing to graph once I simplified, but I had to kind of note all of these other qualities and characteristics as well. That was important. So let's talk about domain, the x values that this takes on. It goes left and right forever. You do all real numbers. That stands in for the infinities. There is one restriction. Actually, there are two restrictions. I totally forgot about something. So here's the big one. X cannot equal -4. That is a big no-no. That's a vertical asymptote. But I also forgot to factor in this whole. And so you always have to go back and check. Oftentimes I'll forget about that and then have to rearrange and open up one of these dots. Okay? -3 itself is a restriction. It just doesn't end up as an asymptote restriction. So here in my graph, I actually don't want to have a solid point. I want to erase that. I'm going to put an open point here, and that takes care of the potential of dividing by 0 early on in the problem. You don't want to equal -3 at all. So those two restrictions go in my domain. The range. And again, that's a way to kind of catch your mistake, which is good. Down forever and up forever, so -infinity to +infinity, but there is actually a pair of heights that are unachievable. You cannot have a height of 1. The asymptote, the horizontal asymptote is there. And then also, you cannot have a height of -2. If I go ahead and shot a laser beam through that height, it misses the graph entirely because there's a hole there. So you have to look at where your hole is because it actually makes kind of this hidden range restriction that you don't know about until you see the graph. So -2. End behavior. This is really important. So as x goes to -infinity, I typically start by going left on my graph because that's how we read them, left to right. The y values here, the answers are zeroing in here on a height of 1. We're approaching that horizontal asymptote, but we're approaching it from the top. So 1.1, 1.01, 1.00000001. All the y values are going to go towards 1, but from above. Sorry about my terrible handwriting there. Then we go ahead and we talk about the other side as x approaches infinity, going to the right. Well, we're approaching that horizontal asymptote as we get very large, but we're doing so from the bottom. 0.9, 0.9999, 0.9999999, 100 of them. So the y values are headed towards 1, but they're doing so from below 1. All right, and that's the process for doing one of these larger rational functions. I hope it helped, and we'll catch you guys in the next video. Thanks.